Okay, so welcome to the DTC seminar. Today we have Ting-Chi Wu from Sierra at the CSU. So brief introduction. So Ting-Chi got his bachelor and master from National Central University from Taiwan and her PhD from University of Miami. So she is now working at Sierra at CSU as a research scientist, scholar, and she has been working on the DTC visitor project since last May. So today she is going to present on her DTC project, evaluating and merging the capability of assimilating satellite hydrometeor retrievals into GSI for HWRF applications. So,
thank you. Can everybody hear me? Okay. Thanks, Chenhua. So before I begin, I would like to take this opportunity to first thank DTC for the funding support, and also thank my host, Chenhua, and Minghu, Catherine Newman, Louisa Nance, and Jessica Johnson from DTC for helping me completing this project on various different aspects. And also, I would like to give my great appreciation to my colleagues in Fort Collins, Milia Zupansky and Louis Grasso, Paula Brown and Chris Kumarol, and finally John Neff. We made a good team in this project. So as Chenhua mentioned, when I joined Sierra in 2014 as a postdoc, and I was given this project that's funded by the NOAA Sandy Supplemental Program to work on assimilating cloud and precipitation indicative observations from satellites into the hurricane core in order to improve its forecast. And during these 2 years, we have developed new data and new techniques. Toward the end of that project, we were encouraged that we should probably bring our techniques into the community so that can be used by more people and also probably be considered by the operational usage. Then DTC is a perfect place to do such a thing. So we apply, and then we are luckily funded, and that's why I'm here today. So the ultimate goal of this DTC project is to bring out the capability that we developed during this NOAA Sandy Supplemental Program into the community by merging it to the trunk depository and evaluating its performance in operational system, which I mean GSI and HWRF. So the new data we introduced is called the Hurricane GPROF. Throughout the talk, I may use HGPROF for short form. I will talk about what the data is and then how do we prepare for GSI data assimilation, and also the added capability to assimilate satellite retrieved hydrometeor data from HGPROF. We'll talk about the implementation of 2 sets of observation operators and also the facilitation to allow HWRF system to use the new data. And finally, the merging and evaluation of the added capability within the HWRF system. So for those of you who are not familiar with HWRF, this is a simplified version of the flowchart of HWRF. So in the beginning, I know this is not the best color for this projector, but so the first component is called atmospheric preprocessing. Essentially, it takes the GFS and GDES data and along with an NHC store message information to initialize the HWRF model with 3 domains. The outer domain was 18-kilometer resolution, and the middle nest was 6-kilometer resolution, and the innermost domain has 2-kilometer resolution. And these 2 inner nest domains are vortex following. In addition to these 3 forecast domains, there are also 2 other domains that's called ghost domains. These ghost 2 and 3 are slightly enlarged from their corresponding middle nest and inner nest for the data assimilation purpose. So after the preprocessing, the next step is the vortex initialization. This is the procedure that the vortex that's within the HWRF, either a previous HWRF forecast or the interpolated HWRF or the interpolated data on the HWRF domain from the GFS or GDES data, or a bogus, will be corrected based on their location and intensity and size using the TC vital data. The outcome of the vortex initialization procedure is a first guess on the ghost domain with vortex corrected. And after the vortex initialization, the first guess is passing to GSI to do data assimilation. Data that are being assimilated, including conventional observations that's available in the per buffer files, and also flight data from TDR or the drop sound from the Global Hawk. Also, satellite radiances under clear sky condition for now. And the GSI is configured as a hybrid 3D EMVAR scheme. Hybrid means your background error covariance is a blend between the static component and background and ensemble component. For the GSI within HWRF, 20% of the weight is given to static and 80% is given to the ensemble, which is composed by the 40-member HWRF ensemble forecast. And in this current setting, there are 2 outer loops used. And within each outer loop, there are 50 inner iterations, meaning that there are 50 linearized approximation during this minimization procedure. And also, the first guess at appropriate time is also utilized to allow observations that span within a plus minus 3 hour window to be utilized more appropriately. After the data assimilation, you will have an updated analysis on the ghost domain, and these ghost domains are then merged with the parent domain and interpolate it back onto the forecast domain. So the next step is the coupled atmosphere ocean forecast. I just want to mention that this atmospheric component of this couple model is the WRF MMN dynamical core, and it's using Ferrier-Aligo microphysics schemes. So after the forecast, the output is passed to the post-processing components, in which the unified post-processing and GFD of vortex tracker will generate products that NHC the National Hurricane Center can then use for operational guidance. So the new data is called Hurricane GPROF. This is Hurricane GPROF is a passive microwave retrieval algorithm based on the Bayesian methodology. And you might have heard of the Goddard profiling algorithm, which is GPROF for short. So HGPROF is a hurricane-specific version of the GPROF. When GPROF is designed to retrieve rain ray and hydrometeor profiles from microwave radiometers. And it requires a database that's composed of it requires a data set that contains both the TRIN microwave imager data and the precipitation radar data. But when GPROF come up with this database, it's only a 1-year database. And also because of the infrequent nature of hurricane, there are not many hurricane scenes in this 1-year database. So what the Hurricane GPROF is different from GPROF, it's by increasing this database to have more data. So now the database is using a 9-year-long data from the TMI and PR. In addition, HGPROF also used this storm position and size information in HWRF to only allow the tropical storm or cyclone pixels in the database to be utilized. Unlike the GPROF, Hurricane GPROF can only be applied to TMI or GPM microwave imagers. Essentially, it will also provide retrieved instantaneous rain rates and 4 hydrometeor profiles only at the tropical cyclone pixels. So these 4 hydrometeor profiles include cloud water, rain, mixed phase, and ice. And each vertical profile has a vertical resolution of 500 meter in the first 10 kilometer and increase to 1 kilometer up to the 18 kilometer height. If you want more details, you can go to this paper by Paula in 2016. She also had very recent developments that expanded this product into a global data set. You can also find it in Brown and Musgrave in 2018. So as I mentioned, there are 4 hydrometeor profiles. For the purpose of data assimilation, we transform them into 2 integrated quantities, and they are the solid water content pass, which I'll call it SWCP for the rest of the talk, and the liquid water content pass, I'll use LWCP. So essentially, these 2, SWCP is a vertical integral of the ice profile plus the upper half of the mixed phase profile. And the LWCP is a vertical integral of the rain and cloud water profiles plus the lower half of the mixed phase profile. So the 2 figures on the lower part is example of the SWCP and LWCP computed from the HWRF hydrometeor profiles. I believe this is a case from Hurricane Gonzalo. So in order to utilize the new data set, we have to come up with the observation operator to simulate it. And while we're working on HWRF, the more we know, we realize that there is actually no cloud condensate in the initial state of Hurricane WRF, which means that the first guess after the vortex initialization passed into GSI is cloud-free. So there's no cloud condensate that we can correct based upon. Then our approach is then to adjust the environment to reach a saturation state as if there is cloud condensate. So the operator is essentially a vertical summation of water vapor in excess of saturation with respect to ice for SWCP or with respect to liquid for LWCP. As a result, we call this operator NOHYDRO, and is a function of temperature, pressure, and specific humidity, as you can see in here. As a first glance, you'll see that these 2 equations are actually identical, except for their summation bounds. You can see that SWCP has a summation bounds from a model level where the temperature is around, where the temperature is 273 degree Kelvin to the top of the model, while the LWCP, the summation bounds are from the model first level to a level where temperature is 253 degree Kelvin. This is because the saturation vapor pressure with respect to ice, which is E sub Si, and the saturation vapor pressure with respect to liquid, which is E sub SL, they are bundled into this equation so that you can just pick a temperature and it will calculate the saturation vapor pressure with respect to either ice or liquid for you. So since this is a new observation operator and new data, we thought it would be interesting to do a single observation experiment to understand how this hydro observation operator works and how the information are spread spatially and to other control variables. So then we created a single synthetic SWCP and a single synthetic LWCP observation, which they are about 0.5 kilogram per meter square greater than the first guess. And the picture on the lower part is showing you the analysis increment from an experiment where we purposely turn off the ensemble component. So this is no hybrid. It's just pure 3D bar GSI, because it will be easier for us to understand or explain the possible physical explanation behind it. So this is a cross-section of analysis increment of temperature, specific humidity, and a model plan view of surface pressure. The cross-section is taken at a latitude where this single observation is located. You can see that for both the single SWCP and single LWCP experiments, the response in temperature and specific humidity are very similar, except their location are in different. The response is occurred in a location that's different from each other. This is as expected because SWCP is a solid component which should only exist at upper levels, while the liquid the LWCP is a liquid form, which is in the lower troposphere. And then we repeat the same experiment by turning this ensemble component back on. So this is the hybrid 3D and infrared GSI, where 20% of static background error covariance is used, and 80% of ensemble background error covariance is used, which is from the GFS 80-member ENKF forecast. So if you go back to the plot, you can see that the location of the response are still very similar, except that there is more spatial variations because of the structures in the background error covariance from the ensemble component. And I would also like to mention that the decreasing temperature and the increasing specific humidity is expected because you are lowering the temperature and increasing the water vapor to reach a saturation state, as the operator should do. So then we put the new data into the system and see how this new data work with the NOHYDRO observation operator. So you already see these two figures on the top, which are the SWCP and LWCP from the retrievals. And the second row are the corresponding first guess. And the third row is the corresponding analysis after the assimilation. And this is also, again, a case from Hurricane Gonzalo at the time of 12Z, October 16. So at a first glance, you can see the analysis is an improvement over the corresponding first guess. However, there exists a consistent underestimation of both SWCP and LWCP. And also in the analysis. This is because the first guess that we used is from a forecast from a previous cycle. And this forecast has already gone through the condensation due to a saturation during either the microphysics process or the cumulus parameterization. So as a consequence, the computed water vapor in excess of saturation using this NOHYDRO operator is much reduced. In summary, NOHYDRO is the first attempt to try to translate observed hydrometeor information into the model variables by adjusting the environment as if there is cloud condensate. It's a relatively easy implementation because changes are only made to the GSI code. The rest of the HWRF stays the same. But the resulting analysis still has no cloud condensate. So this motivates us to actually thinking about how to put condensate into the model. And that's the second operator I'm going to talk about, which is called hydro, naturally. So the goal is we assume there exists cloud condensate in the first guess, and then they will be adjusted by the simulation of SWCP and LWCP. How do we do that then? We use a prognostic variable, which is total cloud condensate from the HWRF Feria Aligo microphysics schemes, and then diagnose individual hydrometeor species. So then the operator is a vertical summation of the frozen or solid hydrometeor species for SWCP, and then it is a vertical summation of the liquid hydrometeor species for the liquid water content path. As a result, the hydro operator is only a function of individual hydrometeor species, as you can see in here. As I mentioned, the CWN is the prognostic variable. We need a partition formulation that will take the total cloud condensate and partition it into individual hydrometeor species in order to use this operator. Besides that, some modifications to the components of HWRF other than the GSI are also required. And here it is. So this is the same schematic diagram I showed before, but I highlighted the three components that requires modification in order to use the hydro observation operator. first, and I will also highlight the changes, the modification we made in red text. So in the current operational configuration, after the vortex the cloud condensate was left out during the vortex initialization procedure. So your first guess is cloud-free, like I said before. What we did is, after the vortex initialization, values of cloud condensate from the previous HWRF forecast are used to populate the cloud condensate variable of the first guess. There is a grid mapping here. As you can see, the forecast is in a forecast domain that I mentioned in the middle nest and inner nest. And we have to map this information from the forecast domain to the ghost domains. And during the GSI data assimilation procedure, the current setting is the existing control variable does not include cloud condensate, which is very natural because there's no cloud in the background. What we did is we include total cloud condensate as a control variable and introduce partition formulation from CWN to individual hydrometeors and its tangent, linear, and adjoint parts because they are required in the minimization procedure. In addition to that, we also add the diagnosed hydrometeor species as state variables. Finally, during this merge process, CWN cloud condensate was left out again. This is because merge was using the same program that was utilized within the vortex initialization. So what we did is, after merge, we keep the GSI updated cloud condensate from the ghost domain in the initial condition of the forecast domain. Here, another domain mapping also occurred. So I keep mentioning about this partition, and what this partition really is I will talk about it now. So as I mentioned, the prognostic variables of hurricane Varia are legal microphysics schemes is not individual hydrometeor species. Instead, it's a total cloud condensate, plus 3 other partition parameters. And they are the fraction of ice and fraction of rain, which are in the unit of percentage, and a rising rate. So in GSI, there exists a partition formulation that can be used to diagnose individual hydrometeor species, given the 3 parameter partition parameter. And this is the partition formulation. After the partition, you will have individual hydrometeor species, including liquid water, mixing ratio, rain, and ice, which is non-precipitating, and also precipitating ice, including snow, graupel, and hail, depending on the rising rate. And this is a relatively simple formulation to get things going for the purpose of data assimilation. During a recent personal contact with Brett Ferrier, who is the developer of the scheme, he said it can certainly be further improved if we would like to consider for future applications. So we repeat the same experiments, but this time using the real data, and this time use the hydro observation operator. Again, you're seeing the observation on the top row, and first guess as second row, and analysis on the third row. On the same case, the Hurricane Gonzalo. So you can see that first guess has too much frozen or solid condensate near the core of the hurricane, while there are too few liquid condensate to the north of the storm center compared to observation. After the assimilation, analysis is an overall improvement over the background, the first guess. It is also an improvement over the analysis that was produced by the NOHYDRO run, if you remember. So to further understand what's the adjustment behind the first guess to the analysis procedure during data assimilation, we do a east-west cross-section along this latitude at 26 north, and we'll plot analysis increment of total cloud condensate and specific humidity and temperature. As expected, in terms of total cloud condensate, the positive increments can be found in the lower part, which is response to increase of liquid hydrometeors. While a decrease in terms of increment is found in the upper troposphere. This is also corresponding to reducing the frozen or solid hydrometeors in the previous plot. And the corresponding responses can also be found in specific humidity and temperature. We think it's reasonable because when you put condensate into the system, you'll expect the system to warm. It will release heat, so the temperature should be warmed, and the specific humidity will increase. I also plotted the same analysis increment cross section, but using the NOHYDRO case as a reference. So you can see that the response are fairly similar for temperature and specific humidity in the lower troposphere, while it's slightly different or much different in the lower troposphere. And in addition to that, you can also see that the increment is about 2 times smaller compared to the results from the hydro experiment. So then we also evaluate our results with GMI brightness temperatures. On the left is observed the GMI brightness temperature at 36.5 gigahertz. And the two figures on the right are the synthetic GMI imagery at the same frequency computed from HWRF first gas analysis using the CRTM, which is a community radiative transfer model. And as you can see, the first gas, in this particular frequency, the ocean appears much colder, which it has a range around 220 Kelvin to 230 Kelvin, while the storm with hydrometeor signatures appear much warmer. So in the first gas, you can see that the hydrometeor are more concentrated near the core and making the storm look more smaller compared to the observed imagery. After the data simulation, because of adding more liquid water content, we see that the analysis now is looking more closer to the observed imagery. And we also repeat the same plot for a different frequency, which is 89 gigahertz. This is a frequency where the ocean appears warm, while the hydrometeor signatures appears cold. You can again see that because of after the simulation, this hydrometeor signature to the north of the storm is more pronounced, while maybe there's still a lot of work to be done to make to really reach what it's like in the observation. So then we do two Hurricane WRF and GSI experiments. In these two experiments, we assimilate SWCP and LWCP into the innermost domain of HWRF. In the first experiment, we use the standard HWRF configuration and assimilate the data using operator NOHYDRO. In this case, all the observations that I mentioned from the conventional and satellite are also assimilated. For the second experiment, we use the modified HWRF configuration and assimilate SWCP and LWCP using the hydro operator. Similarly, all the observations that was considered in the first experiment are also assimilated here. So the only difference between these two experiments is the operator and the modified part of the HWRF. So we picked two cases from the 2014 Atlantic Hurricane Basin. One is the Hurricane Edward, and the other is Hurricane Gonzalo. Because of the availability of the Hurricane GPROF data, we are restricted to, because of the availability of data, we initialized the model at 0Z of 16th of September for Edward, which is around when Edward was already a major hurricane. And then we continue this 6-hour cycling until the last Hurricane GPROF data was available, which is 12Z of 17th of September. And similarly, because of the availability of the data, we initialized Gonzalo in Hurricane Wharf at the 6Z of 16th of October, and then also continue running 6-hour cycling until the last Hurricane GPROF data is available. So then this is adding a new data into the system. We might as well look into how they perform in terms of data simulation. And one of the metrics to look into is cost function. As I mentioned, there are 2 outer loops used and 50 inner loop in each. So in the x-axis, you'll see 102 numbers of iterations. As I point out, this is the first outer loop, and then you can see a jump because that's where the second outer loop, when the nonlinear operator is applied. And I also included a curve from control, which is a standard HWRF GSI, which is a standard HWRF run without assimilating any of the SRUCP or LWCP. So to list it here for reference. And you can see that the initial value of the cost function from the NOHYDRO and HYDRO are much higher than the control. This is because we add more observation into it, and the observation and the first guess, maybe there are some difference between them. And because of this different initial values, a better way to look at the cost function is to normalize the cost function by its initial value. So now your cost function will be ranging between 0 and 1. And what we are seeing here is after this first outer loop, the inner iterations that are the linear approximations are during the minimization it occurred here. All 3 curves has a very good convergence rate. But you can also notice that there is a very much bigger jump from the end of the first outer loop to the beginning of the second outer loop in the NOHYDRO experiment. We hypothesize that it's probably because the linear approximation is not so well for the NOHYDRO observation operator. So if there will be another nonlinear estimation in the end of the second outer loop, the jump may also come up but still be slightly lower than the first jump. But it is common to see there is a slight jump after the linear approximation, after the nonlinear observation operator is applied. So then this is results when we look into the influences on the Hurricane Wharf forecast. I'm showing you the forecast track and track in errors and intensity, forecast intensity as a function of forecast lead time, initialized from the very last cycle of the experiment I mentioned. Top panel is the result from Edward, and lower panel is the result from Gonzalo. You can see there has no significant differences in terms of forecast track intensity between these 2 experiments. And I don't know if this should be expected. However, while I was working on this DTC project, I was also working on another research that we assimilated all sky radiances into HWRF on a different case. And that case is Hurricane Cristobal. When we look into the very first 30 minutes of the forecast and plot a horizontal view of the total cloud condensate, for example, at level, you pick a level, for example, 35. This is the initial time of the total cloud condensate. And after 5 minutes, this is what it looks like. This is after 15 minutes, after 30 minutes. you can see very significant decrease of total cloud condensate. If you then we choose a very we look into it by zoom in this particular scene. So now the magenta contour is plotting the total cloud condensate with a value of around 1 or 2, I forgot, but like around that range of gram per kilogram. And the color shading is the temperature in Kelvin, while the blue and red contour are the vertical motion. This is seen at 5 minutes. So you can see that the cloud condensate is collocated with a much colder spot, which is about 4 degree Kelvin, much colder than its surrounding. And it's also collocated with a sinking motion surrounded by an upward motion. If we look at the cross-section along this longitude, you'll also find that this the sinking motion is collocated with divergence, and the upward motion is also collocated with convergence, which is a secondary circulation that's triggered by the falling of the total cloud condensate. So the conclusion is, during the first 30 minutes, or maybe even longer, but we didn't look much further down in the forecast, due to the lack of vertical motion at the initial time, condensate experiences evaporation, cooling, and precipitation settling. I didn't look into the Gonzalo and Edward case in this project, but you should expect the same response because there was also no vertical motion at the initial time. So, summary. During this DTC project, we transferred the GSI capability to assimilate SWCP and LWCP from the Hurricane GPROF retrievals using 2 different pairs of observation operators developed for HWRF. These 2 operators, including one that's called NOHYDRO operator, which is the first attempt to translate observed hydrometeor information into model state through an adjustment of environmental temperature, specific humidity, and pressure as if there is cloud condensate in the first guess. And the resulting analysis is an improvement over the first guess, although the consistent bias was found and there is still no cloud condensate in the analysis, which motivates us to do the second operator. And this second operator actually needs some modification to the current hurricane configuration, but it directly adjusts existing cloud condensate and results in an analysis that's much more closer to observations. We used 2 hurricane cases to test both operators under a continuous cycling setup. Results in terms of forecast show no obvious differences in terms of forecast track and track intensity. But when we look more into the early part of the forecast, we found this new issue with missing vertical motion at initial time, which lead to cloud condensate decreasing significantly because of evaporation cooling and precipitation settling. So the future work will be more cases are needed because I mentioned Hurricane GPROF has now been extended beyond the Atlantic basin. They are now including more data from all the hurricane basin or typhoon basins around the globe. And we also need more data, data from the sensors or instruments that can observe hydrometeors in order to verify our results. And the issue with the missing vertical motion at the initial time, we were thinking maybe it is possible to diagnose vertical motion from other variables during the initial time. Perhaps continuity equation can be used. Or we can include vertical motion update in GSI for HWRF. However, I don't think this approach is realistic because the MMM dynamical core has vertical motion as prognostic variables. Also, another future work can be to allow cloud condensate cycling in HWRF, because the modification we proposed and I presented in this talk, except for those in the GSI, are standalone procedures that we developed outside HWRF. That means when we run HWRF with the hydro observation operator, we have to stop HWRF after vortex neutralization and do our own thing, and then put it back and continue running HWRF until the merge state, and then do our own program running, and then put it back to the hurricane system and let it continue running till the end of the cycle. So there is a need to directly modify the code within the vortex initialization and merge components in order to include cloud condensate in the HWRF so it can run on its own without being interrupted by external procedures. And this is actually a newly funded project I will be working on in the fall. And finally, the operation is moving toward all-sky radiance assimilation, and I believe HWRF is as well. So in order to do all-sky radiance assimilation, CRTM is essential because CRTM requires individual hydrometeor species and their optical properties, along with other state variables, in order to compute satellite radiances under all-sky conditions. And I believe the modifications we made to GSI are relevant to the development of all-sky radiance assimilation for HWRF. And that's all. And that's a picture of my boy. Thank you. Questions?
We have time for questions. Okay, Evan. Better use this one if you want to
Sure.
record.
So I have a lot of questions. It's very interesting, but maybe I'll try to keep it brief.
Sure.
How do you do the mapping between the first guess and the ghost grid, since the vortex has been resized and relocated?
Yes. So as you know, the ghost domain actually has the same grid spacing to the inner nest. Sorry, the middle nest and the inner nest. They are both either 6 kilometer or 2 kilometer. So there's no problem with the grid size. But the ghost domain is slightly larger than the forecast domain. What we did is we actually take the parent domain and then the forecast domain. And we put for example, if we want to create the hydrometeor field, a cloud condensate field in ghost domain 2, we take forecast from the first parent domain and the middle nest, and replace the values of the cloud condensate in the parent domain by the cloud condensate in the middle nest. And then we populate that values onto the ghost domain. When during that procedure, we take into account that the vortex location may be different. So we make sure that the center is located at the same, at the same geophysical location. And the same procedure also applies to the ghost domain 3. We take the cloud condensate field from the middle nest and populate their cloud condensate field with the cloud condensate field from the inner nest, and then do the mapping so that there's no gap in the boundary, if you call. Yeah.
And so you just account for the change in position of the vortex,
yes,
but not necessarily the change in size. Okay.
So that's why I said there's a need to really go into the code to modify. At first, we wanted to go into the code, directly go into the vortex initialization code to modify, but it's too much for us to do within like a 2-year time frame. So that was our quick fix.
Maybe one more question and then I pass it on.
Sure.
Obviously, there's some obstacles with the hydro experiment, but how close do you think we could be with the NOHYDRO experiment to like EMC running like hundreds of cases with this? What obstacles might there be there to doing that kind of retrospective experiment, that many cases?
I don't know if I understand your question clearly, but are you asking if we are trying to run the hydro experiment, how efficient will it be compared to the no hydro experiment?
Well, no, actually, I'm just asking, could we test the no hydro experiment
no hydro, okay.
with
Yes.
a lot of cases in HWRF now, like in an automated
Yes,
way?
because the modification is only in GSI, and I have already committed the code in GSI trunk, so you are free to use it. The only thing is preparing the buffer file.
Yeah.
Is a site from the GSI source code, but I can provide you the buffer transformation code if you want. And you can also get the the raw Hurricane GPROF data. I think you can get it from, Paula remind me this, but I think it's from AWIPS or NHC has the operational product if you want to test it with more cases.
So it's not like those data are on GTS and
No.
buffer file. Okay,
No.
I didn't think so. But,
When, at the time, it was still experimental.
okay. Thanks.
No problem.
More questions? Okay, I have a quick one. So you mentioned you're working with HWRF. So LW has its own hydrometer.
Yes.
So it doesn't work, or there's some work that has to be done in current GSI to use this with AW?
I think a lot of it really depends on the microphysics schemes you choose, because each microphysics scheme have different hydrometers. For example, they have maybe someone has ice, grapple, snow, and that's it. But someone has other species. So in the GSI code, it can now expect hydrometeor species, but you still need to go into the code to modify it. Only when certain microphysics scheme is chosen, only these hydrometeor can be used. That's my understanding. Yeah.
Okay. Okay, more questions? Okay, the code is inside the GSI master branch now, and it will available for public when GSI new release coming, which is this fall. Okay, enjoying the code?
Thank you.
Okay. Thank you.
Thank you for coming.
Okay, let's thank you again.
Thank you.